Let's try this problem. There's a new little twist in it. So find the maximum and minimum values of f of xy is x squared plus xy plus y squared subject to the constraint that g of xy is equal to x squared plus y squared is less than or equal to 25. So what's the difference here compared to the previous problems we've done in this section? Our constraint is not an equals here, it's an inequality. It's a less than or equal to 25. Let's just draw a picture here real quick in the xy plane. Of course, x squared plus y squared is equal to 25 would be a circle of radius 5 in the xy plane. X squared plus y squared is less than or equal to 25. It's this filled in disk. It's everywhere inside, on the circle itself or inside the circle. So how do we attack this problem? We need to realize that this is actually a combo. It's a 14-7, 14-8 combo. We're trying to we're trying to find maximum values on a closed bounded domain. That's something that we learned about in last section. And so what we're going to do is that we'll find our critical points for the interior, just like we did in our examples at the end of last section, section 14.7, but then for the boundary, remember in 14.7 we did the triangle region, and we did lots of, we had 3 different chunks to the boundary there, and we did one variable optimization each of those chunks. For here, we're going to use Lagrange multipliers instead. So I think this is a good review of 14.7 here, along with throwing in 14.8 stuff going on here. So let's get to work here. So let's start off by, and of course, once we find the critical points in the interior, find critical points on the boundary, then just compare at the end of the day what's going on here. So let's get to work. First thing we should do is find the critical points for the interior. So the x derivative, the x partial derivative is going to be 2x plus y. And the y partial derivative is going to be x plus 2y. Of course, these both need to equal 0, so this is, I should label this that right now we're working on the interior here. Okay, so we need to solve this system of equations. Let's see, if we subtract twice the second equation from the first equation, 2x minus 2x will give us 0. Y, there will be a minus 4y. Y minus 4y is minus 3y is equal to 0. And that gives us that y is equal to 0. Plugging in y is equal to 0 into either of these equations, 2x plus 0 is equal to 0, shows us very quickly that x must also be 0. So this gives us that the origin is the only critical point on the interior. Okay, so we've done the interior. The only place we have to check is the origin. Now we're looking for critical points on the boundary using Lagrange multipliers. So once again, we'll be using this equation here. And so once again, let's see, we've already calculated out, the gradient of f, even though we didn't write it down that way, because we found the partial derivatives. So gradient of f is going to be 2x plus y, comma, x plus 2y. and then the gradient of g. So take the x partial derivative here will be 2x. The y partial derivative here will be 2y. Okay, so at this point then our Lagrange equations. So gradient f is equal to lambda times the gradient of g. And this will give us, so 2x plus y comma x plus 2y is equal to lambda times 2x comma 2y. Okay, really I should be separating out this into two equations because it'll be hard to kind of make headway without that. So 2x plus y is equal to lambda times 2x, and x plus 2y will equal to lambda times 2y. Okay, so these are the equations that we need to solve for here, along with, of course, the constraint that g of xy, so the x squared plus y squared, we want this to exactly equal 25 right here. So we have three variables, x, y, and lambda, and three equations. The way that I'm going to solve this, it might seem like a scary thing, you know, there's variables flying all over the place. I'm going to make the following change here. So I'm going to get rid of the lambda, and how I'm going to do that is that this first equation here has a lambda times 2x. This second equation has a lambda times 2y. And so I'm going to want these to be equal to each other. If I multiply this by y, I get 2 times lambda xy. When I multiply this by x, I get 2 times lambda times xy. And so these two will be equal, and I can set them equal to each other. But if I multiply this equation on the right by y, I also need to multiply this equation on the left by y. And similarly, I need to multiply both sides of this equation by x. So what this accomplishes then is this would be 2xy plus y squared is equal to 2xy lambda. But 2xy lambda is also equal to x squared plus 2xy. Okay, so if this is equal to this and this is equal to this, then this must equal this. And so let me just kind of cover that up so I can do some calculation with it, because on both sides I have let me just recopy this. 2xy plus y squared is equal to x squared plus 2xy. So those two xy's cancel, and I'm left with x squared must equal y squared. Okay, so our next page of our solution, we're down to just x squared plus y squared is equal to 25, and x squared is equal to y squared. So if we replace y squared with x squared in our equation, we get 2x squared. X squared plus x squared will equal 25. And x squared will equal 25 over 2. And so then at this point, x will be plus or minus the square root of this. And so that's plus or minus 5 over square root 2. And if if y squared is equal to x squared, y squared also has to equal 25 over 2. So y is going to equal plus or minus square root of 25 over 2 is plus or minus 5 over square root 2. Okay, so these are solutions, and so there's two possible picks here for x, there's two possible picks here for y, and all of the combinations here, excuse me, all of the combinations here are, do work as Lagrange multiplier critical points. So we found one critical point on the interior, and so our list of critical points that we have to look at is going to be, 0, 0, and then all possible combinations of x being plus or minus 5 over square root 2 and y being plus or minus 5 over square root 2. So 0, 0, 5 over square root 2, 5 over square root 2, 5 over square root 2, negative 5 over square root 2, negative 5 over square root 2, 5 over square root 2, and negative 5 over square root 2, negative 5 over square root 2. So these are our 5 candidates. I think the last section I made a list of candidates. So let's write that out. And so now we just have to take each one of these critical points, and plop it into our f of xy equation. So when we do that, so f of point, so when we plop in 0, 0, 0 squared plus 0 times 0 plus 0 squared gives us 0. When we insert in 5 over square root 2 and 5 over square root 2, well, anytime we see this x squared plus y squared, we know that x squared and y squared are both 25 over 2. So really, what's going on here for all of these, so when we write f of xy is x squared plus y squared plus x times y, it's really x squared and y squared, well, I can just do this instead. X squared plus y squared is equal to 25. Maybe that is simpler. So it's 25 plus x times y. This will just make our life a little bit easier when doing it. So, of course, this doesn't apply to this one. This only applies to the ones that are on the boundary, the points that we get from doing Lagrange multipliers. Okay, so what's going on here? We get, for this point, 25 plus x times y, and this will be 25 over 2. And all of that simplifies to 75 over 2. Of course, you can definitely checklist yourself to make sure I'm doing this right. This one will give us 25 plus this times this, and that'll be 25 minus 25 over 2, which is 25 over 2. This one will give us, similarly, 25 over 2, and this one will give us 75 over 2. And so let's finish off the problem. Find the max and min of this equation subject to this constraints. The biggest value that we see here is this. So the max is 75 over 2, which occurs at the points 5 over square root 2, 5 over square root 2, and negative 5 over square root 2, negative 5 over square root 2, and the minimum is 0 at the origin. Okay, so I think this was a good problem. It tied lots of concepts together.